All right, I think we can start. So hello everyone, thank you for being here. My name is Damien Bataille. I'm lead software engineer. I've been at NVIDIA for 5 years now. I come from visual effects. I work in visual effects for 14 years. And I'm leading a project called Neural Face. And yeah, we'll talk about that today. There's a lot to talk about. So let me introduce you to Nathan. Nathan here.
Yeah, my name's Nathan Hubler. I work in the developer technology group. So we work on integrating new technology into rendering engines in real time and performance optimizations.
Hello, I'm Bernardo Antoniazzi. I'm working with the Lightspeed team and I deal with character creation mainly. Right. So before we start, I have a quick disclaimer. So what we're going to see today is a case study on how to actually use AI for real-time rendering. This is an experiment. It's an experiment that is producing very promising results and is attacking directly, a problem that's been around since the dawn of rendering. So how do we make realistic characters? And we really hope that you guys, will be able to take away the learnings and the approaches that we are been experimenting with to apply AI to solve your problems, in your projects. All right, so let's start with the big question. So why are we actually, working on neural-based rendering? So one of the most challenging aspects of modern game development, I would say, is actually achieving human faces. And they require very advanced rendering techniques, like to name a few, like subsurface scattering, we need rendering, specific kind of rendering for hair, simulation, micro displacements, and it's very difficult, And on top of that, animation adds an extra layer of complexity to the mix, basically. So we really need to pay attention, for example, to eye movements, micro expressions, and find very, very precise deformations to convey emotions naturally, basically. So there's a lot of time that gets put into development to try to tackle all these aspects, but there's still something that is missing. If we look at the characters that we work on, in the last few years, they all show great advancements in rendering and animation techniques, but there's still something that is missing. I mean, we feel that we can still tell these are 3D characters basically, and this is 3D animation. So they're still not real human. There's always that little 10% that is still missing, right? So we really need to do something about it. So how do we solve this? Well, I think that AI can definitely help. So this is where actually neural face technology comes in. So it represents a shift, a very fundamental shift, I would say, in how we approach character rendering and facial animation. So it's a major change that we think will most likely actually reduce manual workload, for our teams, and while improving realism in ways that were previously impossible. So today we will discuss the neural face pipeline that Damien has been working on and I'm spearheading at NVIDIA. All right, so let's start with the workflow. So we have two pipelines. We work with through different distinct pipeline. So the first pipeline is an offline pipeline. So this is where we actually generate, the training data, and we refine our model. Then we have a runtime pipeline, and this is where actually we take the very complex model that we actually generate, and we distill it, we compress it, and we kind of narrow, its focus, so that it can actually run in real time in our engine. And actually, go back. The offline pipeline, well, let's start with an overview of the offline pipeline. So what do we need really to start, training our model? We need 15 images. So that's all it takes basically to for us to build a model. So we need 15 images of our character with a neutral, expression in a neutral lighting environment from multiple camera angles. This is really what we need. And we will take these 15 images and we augment these images and enhance them. And we will actually come up procedurally with a massive data set of over 35,000 images. And these images actually will show the face of our character with different facial expression, different lighting scenarios, and also we'll simulate some sort of occlusion on the face. Let's move more into details. So we can start with a picture of an actor, and that's actually straightforward. We know that most, AAA game production actually capture the character. So we have extensive data sets of these characters, from the photometric, capture system, for example. We have performance capture. I go as far as saying that even HMC data could be used, right? So we can take all this data and actually train with high accuracy, our model. And definitely enhancing, the realism without any extra overhead, really, because we already have the data available. But there are also a lot of production that don't use characters, right? So let's say we have a character that is original, is hand sculpted. Well, this is not a problem. We have a solution for this. So what we can do, we can just start rendering out 15 images of our character from the engine. In this case, this is one of the characters that we work on for our demo, Zorah. And this is just a custom metahuman character in Unreal. So what we were able to do is just create a simple animation that we can apply to all our characters. So it's something that is repeatable, And all we need is basically 3 head angles for our characters. So the character looking up, looking straight forward, and looking down. And we are going to capture different body rotation. We capture the degrees are around 70, 80 degrees, 45, 0, and the negative values. We go to 70 because 90 degrees can kind of be problematic for the model. So we don't want to go at an extreme angle. And all we want is a neutral expression under neutral lighting condition once again, so no harsh shadows on the face. We want a camera lens that minimizes distortion. So like a 50 millimeters equivalent is going to work fine. And we need to see the shoulders. And we capture this image at 2K resolution.
Same.
All right. So what do we do next? We actually run these images through a process that we call uplift. So we will use generative AI to actually make the character look realistic. So how does this work? We're actually going to take all our renders. We're going to run them through a diffusion model. And after that, we're going to process them through a combination of tile and depth control nets. So this is the time, really, where we want to relax the parameters of our model to allow the model to go crazy, basically, and add all the details to make the face realistic. But at the same time, we need to be very careful. So we want to, at the same time, constrain the parameters so that the output is not a character look anything like the original one. So this is it requires a little bit of tuning to make sure that the appearance of the card is actually preserved, after the uplift process. And this is actually an example of how we can achieve this using Confi UI. So the image will just go through the simple standard diffusion, model. And the final result, after going to the tile and depth control nets, is something that we believe is more realistic. It actually, helps, to improve the realism of the character. One thing to note is that we actually created custom weights to control high-frequency details and low-frequency details for the character. So for high-frequency details, the pores and the wrinkles. And for low-frequency details, is actually the structure of the face. So we want to make sure that the structure is exactly, it looks like a better version of the previous character. All right. So this is the before and after. So we feel that the uplifted version looks significantly more lifelike and achieve a higher level of realism. And these uplifted images are now the base, the foundation for the next step. That is that data duplication process. And Damien will actually talk about it in detail.
All right. Thank you, Bernardo. So the next step is now that we have those 15 images that are photoreal, if I can say, is we need to create the data set, right, to train the model. Why do we need this data set? So we need different facial expression, different lighting, different occlusion for the model to be able after to, swap the face, right? So to do that, we have an automated pipeline. Same, we are using Confi UI here. And let's see that. So first, what do we use Confi UI? Well, this is, I don't know if anyone here is familiar with ConfUI, but this is pretty easy to extend and create some custom node. So this is what we did for this project. And after, this is the perfect tool to train some AI model, right? So if you need to process like images with like different AI model, this is a perfect tool here. So we use it to create like the workflow for the data duplication. And I will explain actually each step of the data duplication to have like this whole data set. Again, we are starting with 15 images, and at the end we have like 35,000 images. So first, so here this is the graph in ConfUI of this workflow to generate the data set. Again, this is 100% automated. So you just give an input, and the output, you have like a data set. So this graph can be scary when you look at it, but actually this is just a graph that have like multiple steps, right? And I will explain those steps here. So the first step is to have a different lighting. So as you can see here, I input one images, and this is generating a different lighting. We use a model called IC Light, and this is taking like just few seconds or even less to give us like a different lighting. And we do that for every angle of those like 15 images. So you can see here, a video where we have like different lighting for the character. All right, so the next step after that, this is to animate the face, right? So we need, like I said, we need different facial expression here. So we use a model called Live Portrait. So what we do here is we input an image, and we have some driving videos that have like facial expression. And at the end, the output of that is like that we have some video that have the same facial expression that the driving video coming from the image, from the input, right? The end result is like around 150 videos of like 9-10 seconds. Added to that, because we have 15 images of different angle, we also need the angle between those angles, right? So while we generate those like facial expression, we also like ask the model to rotate the head a little bit at the same time. So we have like a rotating head. We're doing like some facial expression here. I can show, So the next step here in this data duplication workflow is to segment the face. So why are we doing that here? When we train the model, we ask the model to train only the face, right? We don't need to train the model on the shoulder, for example, or like the hair, at least as of today. So this is why when we give the images to the model, we give also a mask saying like, oh, you need to train only on the face. So to do that, we need to segment the face, and we implement a custom node in ConfUI. We use a model called FARL, and this is working pretty well. This is a little bit slow, but we are working on something else to have like a faster segmentation. Okay. And here an example of the implementation. You can see that this is working pretty well. So this is like segmenting the face automatically. And here a result of, for example, some images of the data set. So this is properly segmented, like on the forehead and around like the face. This is not taking the neck or anything else. So this is pretty clean. After the next step here, when we have all of that, this is to extract the face. When I say extract, what we want here, we want to have the face in the center of the image with the eyes also in the center, the noise in the center. Why we do that? Because when we train the model, this is actually easier for the model to understand the face when you have all the eyes in the same place, the noise is at the same place. So this is why we also implemented some custom node in a conf UI. So we use two models here. One to detect the face. It's called like S3FD. So you give an image. This is detecting the face in the image, like a building box. And after we use another one called Feign, which is like a face landmark, meaning that it will detect where is the noise, where are the eyes, the mouth, and this is how after we can like extract and center the face on the image. And the next step after that, this is to add some facial occlusion. Okay, why we need to do that? When you are in a game, obviously your character will go behind some object, or you can have another character in front of your character. So the model needs to understand that. So here we implemented another custom node that just adds some random custom facial occlusion in front of the face. And this is helping the model after to understand occlusion in front of the face, right? So we do that randomly on the dataset. I think like one fourth of the images have facial occlusion. And yeah, and this is like taking like few seconds also to run. And the last step here, I did forget to mention that the problem with actually live portrait that we use to generate like the facial animation, the output is 512 pixel. So here, as a last thing, we upscale the result, like the whole data set, to have like a 2K result, to have 2K images, and after we are good to go. So we have like a whole data set with like 45,000 images with different facial expression, different lighting, different animation, and a 2K resolution. So here's some like example of what we have. So keep in mind that this, like I say, we start just with 15 images, and we have this type of result here. So you have like a character that just talk with a different lighting and different facial expression, and sometimes some occlusion. Right. So here an example with an occlusion in front of it. And the last one, yeah, just the character talking with, I guess, like a 45-degree angle. So now that we have our data set, we need to train the model, right? So we implement the whole code in PyTorch. This is obviously working on multiple GPUs, and we have part of the code is accelerated with QPy. I don't know if people are familiar with QPy. So this is like a drop-in replacement from NumPy, right? NumPy are run on the CPU, and QPy are run on the GPU, right? So this is faster for some like operation. We use also QPyX, which is like a SkyPy on the GPU, and QSIM, which is also a library to process like images on the GPU, right? So when you have everything on the GPU, this is obviously faster. Let's talk about the model here. The model that we use for neural face is just an encoder, decoder, pretty easy to understand here. So we have one encoder. This is encoding face A and face B, right? After we have like those images in a latent space, and you have two decoder. So the decoder B will decode the face B, and the decoder A will decode the face A, right? Easy here. And what's happened here? So how are we doing the swap? So we just use the decoder A to decode the face B, and because the decoder A was trained as decoding the face A, the result is that we have all the feature of the face B going on the face A, and that's it. This is how this is working. So here an image of the trainings with like all the lost. So we use TensorBoard to see like work in progress result, how long time this is taking and all that. And so when we have the training done, we have a checkpoint, right? A PyTorch checkpoint. And what we do here is we export the checkpoints to a Onyx format. So Onyx is it's an open neural network exchange. So this is a format that you can use to exchange your AI model, right? So you can like export, for example, from PyTorch, and after you can import or convert that to using TensorRT, for example. So this is great, like if you want to exchange your model in multiple, like with multiple framework and library. We do an export to FP32 or FP16. So what is the difference? So FP, this is like full precision. When we do an export of FP16, so full precision 16, it means that you have half of the precision of FP32. It means that your model is lighter, right? And so this is faster after for the inference, and this is also taking less memory. Okay, and as of today, we output the face as a 640 pixels, but we are working on a solution to have an output of 1K or 2K resolution. And from there, I will show you a result. So this is a Zorah character, okay? So this is a work in progress. Like we said, this is a research project, so there's still like a lot of things to work on. But you can see the difference here between before and after. And yep, and from here, I will introduce Nathan that will talk about a lot of things.
Yeah, so we had the runtime pipeline integrated in Unreal, but to kind of prove out this idea and maybe find some different edge cases and experiment with different types of content, we wanted to integrate it into something that was a real-world production engine with production-level assets to see what kind of content an uplift we could achieve. Especially since, some of the examples that Damien and Bernardo showed, they're actually starting from very strong content to begin with. So we partnered with Bethesda to take some characters from Starfield, and just as a science project, so not as something we were actually planning to ship into production, but rather just to experiment and see what sort of gains we could get, integrate it into a branch of their engine and try and run some of their data to our pipeline and see how it performed. The integration process began in December 2024, so a few short months ago. Bethesda gave us access to the core assets and whatever pipeline tools we needed to extract the data that we needed. They provided some scripting to give us the neutral lighting and pose and camera animations to generate our training data. And they did some work to provide some auxiliary data that we needed to do some data normalization on the rendered output that I'll talk about later. We worked with Bethesda to actually integrate the code side of things at the runtime. I will say the programming integration of this is very, very lightweight. It's took about 2-ish months with myself not really knowing anything about the engine to begin with. And I want to take a moment to say a huge thank you to the team at Bethesda for making this possible. They were tremendously helpful, especially since we started the work right in front of Christmas break, and they really filled in to help unblock us on a lot of stuff. So here's a quick still. This is Andrea, who was a key NPC in the Shattered Space DLC. We chose this character for a couple of reasons. One, it as a main companion character, it had a lot of animation and dialogue, so we could really push the bounds on how well this tracked animation and kind of interesting characters in different scenes. She also doesn't have a lot of complications from accessories, hair, different things that actually the uplift system handles relatively well, but would have been a complication when we were trying to get first pixels working. So this is kind of what the runtime integration looks like in the rendering pipeline. What you're seeing is kind of a series of small stages divided into 3 phases. We start with some sort of data preparation and normalization. Then we run our inference to generate the uplifted data. And then we do some post-processing, color correction, and compositing. We inserted this at the top of their post-rendered post-processing pipeline. So as soon as the scene is lit and shaded, but before we apply any upscaling, and especially before we do any sort of transparent or image-based effects like particles, alpha blending, depth of field, to make sure that we have the cleanest image possible to do the uplift. So I'll go through these different sections one at a time, or in groups rather. The other interesting thing here is, so at the top you see the gray boxes. That's all the input and output we need. So as I said, all we consume from the rendering engine is a rendered frame buffer. And then we need some calibration data, which I'll talk about in a little bit. Optionally, we also rasterize a mask of the character, which helps assist the compositing. And the output is just the exact same frame buffer we get in. So it's almost the perfect pluggable post effect. So looking at the runtime integration, the first phase I talked about was data preparation. So there are two important things to do here. First, we have to do what I was talking about, the normalization. So the input needs to look like the training data we got. But in most game engines, so we actually focus on kind of a conversation mode where the character's mostly restricted, but even still there's a lot of head rotation, movement, animation. And it's very important to normalize data so that you're diverging from the characteristics of the training set as little as possible. In the case of Facelift, what we found is we really wanted to make sure that features like eye separation and position the frame and the relative position of the mouth were maintained. So in order to do that, we originally experimented with an image processing system that does facial recognition to identify those points, but that's another network that needs to run, is expensive. And that's actually really convenient when we were working with video data input. But realizing that we're in a rendering engine now, we can use the animation data and the skinning system to generate that ourselves. So instead, what we use is a series of calibration points. There are 3 clusters, one for the left and right eye and one for the mouth. And in the content tools, we just tag a couple of vertices that kind of circumscribe each of those features. Then then at runtime, we run them through the bone and animation system to get a screen space position for all those. We compute the centroid, and then we do some linear algebra to get an affine transform, basically a crop and rotation to normalize the data. So that's what you see on the top here. It's actually not the best example because I was trying to get a capture where her head was tilted and I couldn't, but you can imagine just kind of it takes that and kind of focuses it in so that you can see the image on the left up there is kind of similar to what we were looking at in the training pipeline side of things. Then the other thing we need to do in the next pass is we need to transform the color data to what we want. So I talked about consuming data from the frame buffer. Obviously, we need to account for any exposure correction. We need to go from linear scene referred space to sRGB displayed referred space. And we've also found that de-interleaving the color data from RGB pixels to separate red, green, blue color planes tends to improve the behavior of the inference network. So we unroll that before we feed it into the inference. For the actual inference side of things, we use a tool called TensorRT, an API called TensorRT, that is, in theory, a hardware-agnostic wrapper for executing inference networks. So it consumes an Onyx network, like Damien mentioned earlier. Then the API will kind of compile that network as it needs and optimize it to run on the hardware into what we call an engine. That's the actual executing code. So we actually use an experimental version called TensorRT JIT internally. This is still an area of active research to kind of find the best way to generalize some of this. But the upside is that you don't have to write any CUDA code to make this work. You just basically, you load the Onyx file, which is an opaque data blob. You feed it into the TensorRT API, and then you have to feed the buffers in using CUDA interop. But aside from that, it's pretty much hardware independent. We were running it on a 4090, but there's no reason why you have to concern yourself with any hardware-specific optimizations or functionality. It should be generalized over any hardware that TensorRT supports. So yeah, the only one thing you need to pay attention to is dealing with make sure that you're doing the right thing so that DirectX CUDA interop works correctly. It's not hard, but it's something that game developers generally don't do. And then the output of this stage is just a color buffer and then an alpha channel that contains an inferred mask that roughly corresponds to how confident the model is that the different texels correspond to valid face data. So once we've done the inference, the last part is kind of the correction and compositing. So one thing that we found is sometimes helpful is to do color correction. Basically, the model does, as Damien said, we try to do amplification to show different lighting environments, but there can tend to be still a little bit of bias that captures some of the, the coloration, the lighting of the initial training data. We found that mostly goes away using a very classic color correction algorithm. It's the color transfer between images technique from Reinhardt et al. 2001. All we really do is we project the color data into a decorrelated color space using a matrix transform. We build some local statistics around each pixel, and we try, and then we do the compositing. We try and move those statistics to match the similar data in the input frame. You can kind of think of it as like a very early version of style transfer that doesn't actually involve inference. We also do some adjustments on the image mask that come out of the inference. We do some dilation just because there are some cases where it has lower confidence on like interior details, like around eyebrows and eyes and things. It's not really that critical, but it kind of helps polish things up a little bit. And then the last thing is we also rasterize a mask using the exact same geometry from in-game. And that acts as kind of a backup to the inference mask. So in case where the mask is, not zero confidence, but like, 50% confidence, we cross-check that against the rasterized output to help give us the data we need. You see here at the top, we're missing like the eyebrows and the eye features, but that doesn't actually matter because the confidence in the inference mask there is good. So this is another optional step, but it can be beneficial at times. And then we use all that information to choose what pixels to blend and what not, and to recomposite them in the frame buffer. The bottom image, you see the unmasked version of the output. So it kind of has that cool hallucinated, invalid data stuff around the edges. But you can kind of see this is what the footprint of the actual inference will look like in the frame buffer. So going back to the actual integration to Starfield, I divided into kind of two sets of requirements. We have the content date requirement and the engine requirement, the code requirement. So from the content side, it was pretty light. We just needed some scripts to generate, the 15 training poses, and we needed the calibration points that you see on the side there. For the calibration points, it was since we're doing this on a short timeline, we didn't want to like retrofit their tools, so we just built a system that they put in some dummy animation morphs, and they did one for each set for each eye and the mouth, and then they bumped 4 vertices. And so at runtime, we just load their animations, and we found these tagged codes, and we find the vertex indices, and that was all our information. So this was the easiest part of it. I think it probably took like maybe 2 weeks, really a week for them to understand what we needed, and then another week for them to get us the data. So extremely easy. The engine requirements were also actually kind of pretty easy. It took some time to understand how to plug things into the engine, but the runtime integration, again, we had to add the different stages I just discussed to the rendering pipeline. We had to extend their RHI to support CUDA interop. So in particular, we needed to make sure that the buffers that we were passing between TensorRT and the engine were created with the heap flag, the shared heap flag, so that shared data could be used. And we also needed to make sure that we were synchronizing properly between the GPU queue and the CUDA pipeline. This is important because you need to actually make sure that the data is fully flushed to your rendering buffers before you copy it out for CUDA to use. And then likewise, we have to make sure that the inference is fully drained before we copy it back in. Does induce a little bit of overhead. That's something that, you know, we would like to address in the future from a kind of a driver perspective, but not a big headache. The biggest issue for us, and I think it took the longest time, was actually generating the calibration points, the skinned calibration points I talked about before. And not because there's anything hard about this, but because their engine was simply not built to give us the data we needed where we needed it. So for one, there's no CPU skinning path. This is something we had on Unreal, but they do all of their skinning on the GPU side of things, which normally we'd love. It makes perfect sense. But the problem is that their engine also couldn't do GPU readback very efficiently. It was able to be done, but we would have to wait 3 frames worth of latency because they try and pipeline anything. Again, for perfectly reasonable reasons. And even if we did that, there was a good abstraction between the game logic and the rendering side of things, so that they never really needed to track which buffers came from which objects. They just had clusters of renderable objects. So actually figuring out what vertices after their skinning process correspond to what we needed ended up being kind of challenging. Probably the right way to do it in the grand scheme of things, but not on kind of the short prototype integration we were doing. So instead, we just copied a lot of their shader code and re-implemented it on the CPU, which wasn't ideal, but it ended up working really well. And part of this wasn't a big performance concern because we're only dealing with skinning maybe 12 vertices at a time. So it took a lot of time to figure out what the right thing to do was, but once we did it, it went very quickly. So I'm going to show some performance numbers real quick. As Damien has showed earlier, right now the model size per character is pretty large. It's 1.2 gigabytes. That's all the weights that need to be loaded. Performance, so for the kind of pre-processing pass, it's almost as nothing. It's, a few fractions of a millisecond. Inference on a 4090 was about 6.25 milliseconds, which is pretty substantial, but for something where you're doing like a close headshot, it's not the end of the world. We thought it was pretty viable. This is, a case where you might be able to afford to drop from 60 FIPS to something lower. And then post-processing was, about a millisecond. A lot of that comes from doing the filtering on the output mask. But it's worth pointing out there is a lot of low-hanging fruit here. So we're not using any of the new FP8 or FP4 formats, which is what we store the weights in. And if we switch to, FP4, for example, we find that we get good image quality, which with neural inference, generally quantizing your weights to smaller values can be very successful. We could reduce that model size from, 1.2 gigabytes to 300, 400 megabytes, which would be a dramatic savings. Likewise, inference itself is largely bandwidth limited, so you would see a similar, maybe not a full 4x improvement, but a massive reduction in the cost of the inference as well. So, again, this is, as we said repeatedly, this is very early days in the tech, but I think based on the pure prototype implementation we have, this is extremely promising. I also want to take a quick moment to call out Nsight Graphics and Nsight Systems, which were extremely critical for being able to profile and benchmark this hybrid workload where we're dealing with not just with graphics queue stuff, but also stuff that's being handed to CUDA compute contexts. It was very useful to have a tool that understood how to work with CUDA workloads and could actually show timing synchronization between both the DirectX queue and compute at the same time. And if anyone wants to experiment with this, I highly recommend grabbing these and putting these in your toolbox. So we're going to finish by showing a quick video demo of the results, and I'm going to hand it back to Bernardo to talk about some future work. So I wasn't sure if we had audio, but that's not a big deal. So in this case, you can
surrounded by such a remarkable group of people, present company included. It has been a very long time since I have been someplace that could possibly feel like home. There are worlds beyond count out there, but that feeling is rare and precious.
So yeah, we think the results are pretty impressive. I think one thing that I really want to call out here is that this tracks both the environment lighting and the expressions of the character really well, and that points out something that I think is good to be aware of. Since this is a purely image space with a little bit of bone data as well, it is composable with basically any animation system. So Starfield uses vertex morphs to do all the facial animations, and we didn't do anything special to make sure the model is aware of that character's animations. That's all purely derived from the video data. This is where we'll work with something like audio to face or really anything else you can think of. So it's, again, extremely pluggable. And I think that's it for the runtime stuff. So Bernardo, if you want to wrap up.
Great. Okay, so just to wrap up, I think that this technology can have a lot of uses. We definitely think that initially we can definitely start. Hero characters would benefit for sure for using facial uplit and the neural technology. After that, we think that once we're able to actually compress more the models, NPCs will be the next logical step. They will benefit from a visual standpoint, but also from the animation standpoint, of course. And we can see also other applications, for example, for game remasters, when we want to actually appraise characters from that are existing. And also a lot of applications I think that we're going to see in the future are going to be about avatars and virtual assistants, all these kind of things. And again, once the model is going to be, the whole process is going to be even more streamlined. We will be able just to have a user just apply, upload an image, and then we will be able to generate all the data that we need to train the model kind of in one go. Talking about animation, I think that this technology can actually kind of bridge the gap between raw capture and actually the final result. Because if we are able to train a model directly from the actor, then even if the animation, the source, the input data is not great, what we're going to get out of it is actually super detailed animation. So we're talking about all the subtle deformation of the face, wrinkles, and everything else. Again, with the proper resolution on the model. So we see it like a gigantic advantage, I think, on the animation and the savings in terms of cleanup, for production. Also, I've been in production where the actor was not able to come to the stage to capture performance capture. So at that point, and it would perhaps they're just able to send a recording on a voice line. So we can use procedural systems, animation system like NVIDIA audio to face to generate a solid base for this to drive the model again. And so yeah, we feel that this is going to be allow people to capture animation easily and cheaply and create a very good quality output. And without talking also about localization, for example, if we just want to plug in different voice lines, then the model automatically will be able to convert and you do lip sync, but it's going to be a much more advanced version of the lip sync. So this is it for us. We're actually looking forward to see to what you guys can come up with this kind of technology, and we would love to. We're definitely excited about it. It's still at the beginning, but I think there's a lot of potential, and I think that it can make a big impact. So, yeah, if you have any questions, now we can start the Q&A.
One. Can you hear me? Cool. Thank you. First of all, thank you for great work. It looks extremely inspiring. It's very cool. I have several questions. Please stop me if I become to answer. So my first question is, diffusion models are great things. It's basically like modern oil, but one of the biggest issues with current state-of-the-art diffusion models is consistency. And I have two questions about consistency. First one is, if I'm mistaken, during like data preparation pipeline, using some network which generates facial expressions from like neutral face. And for example, for me personally, if I like raise my brows, I have like wrinkles, and it will be like same number of wrinkles for my different expressions, but it's hard to understand how many wrinkles I have like from neutral. And same, for example, for my eyelid, I have like a little bit of skin issue on my right eyelid, and its issue will be like on the same eye blink expression, but it's hard to understand is it like from neutral. So my question is, have you faced like problems with facial expression consistency during your pipeline?
Actually, that's a good question. Do you want to talk about the slide that we didn't show here?
Yeah, I mean, there was a...
We can show it here.
Let's pull up the slide. So this is an issue with diffusion in general. So this is mainly for the details more than for the wrinkle per se. So when you're using diffusion on models, there's an issue with what I call diffusion noise persistence. That is actually where the noise is more relative to the camera instead of being attached to the model. So that's definitely an issue, and we're looking into solution, perhaps trying to project the noise directly to the geometry and regenerating the details. So this is definitely an unknown issue. Right now, the steps that can come after, kind of minimize the issue, since there are some steps that Damien actually described where the size, the image gets down res and then upscaled again. So all these fine details actually get a little bit reduced, and the consistency get kind of removed automatically. But to me, I mean, what we want to do next, and what I personally think is going to be more beneficial, is actually you use real data. So use the data from an actor.
Yeah.
So do a proper capture with facts and everything, and then use the data from the capture to generate the model. That will ensure consistency. That's why I say for hero characters, I think that is where it's going to shine, because we have not just the data from the photogrammetry system, but also performance capture. We have tons of videos, reference videos. So that's going to make the character look exactly like the actor. And we feel that, as I said, even with the source animation that is not as fine as it is not proper for decapture, for example, stuff like that, we will be able actually to drive a face that is going to look very believable.
I see.
And to add to that, like as of today, we have this whole pipeline of data duplication and like create some like video with new facial expression and all that. And the goal here is also to reduce this pipeline in a way that you have less step you have less you have like some like more you will have more consistency between like the beginning and the end. If you have like a lot of step in between, you can lose this consistency. So this is why we are working like on that to also reduce all those steps, right?
Thank you. My second question is, again, please stop me if I ask too many questions. Do you think correctly that like main transfer network takes as input like raw screen space render of a character, right? And like outputs like enhanced version of character, right? Do you have any problems because of like not the skin but of like hair stuff, like facial like accessories? I mean, do you like take it into account or not?
Yeah. So as of today, we only use like the beauty like as an input, right? But we are working on like a new model where we can use like more data, because here we have the 3D, right? We have like, so we can get like the G buffer, we can get like the normal, we can get like all those data that as of today we don't use. So so we are working on a model that where we can feed not only the beauty, but also like all those 3D data that we have. And from there, it will be like more precise and also, I guess, more better in terms of like training and all that.
Mm-hmm. I see. One more question about model. If I'm not mistaken, you are using some kind of, what I understand from image, some kind of like dual decoder system, right?
Excuse me?
If I'm mistaken, you are using, if I'm not mistaken, some kind of dual decoder architecture, right?
Yeah.
Why not just to use like simple unit like? Why do you need like two decoders?
I didn't get the question.
He's wondering why we're using the A and B decoders.
Yeah. So we use the A/B decoder because this is actually the fastest way in terms of inference So like when we integrate that in a runtime, this is like this is taking like few milliseconds. Where like if we use like other type of model, like for example, I know like a diffusion model, we cannot have this type of like speed at a runtime. So the autoencoder is like I guess as of today the fastest way we found to do for the model architecture.
One more question, more about like project likewise. Sorry, it's my last question. Do you think it will be like some kind like of closed box tool? So for example, you just put like input phase, you go get output phase, that's it. Or you think it will be like open-ended tool when user can like prepare training data by themselves? For example, because Starfield is a great example. Again, tell me if I'm wrong, but I think system can like have some benefits if, for example, a lighting simulation will be not from like diffusion model, but from like engines themselves. So will you like get for user like ability to train from their own data?
Why don't we follow up after the talk because we can discuss a lot more in detail.
Yeah.
Ah, cool. Thank you very much.
Yeah, absolutely. Thanks.
Hi, great talk. And my question is, are the two autoencoder decoder training separately? If so, and how to keep the latent space similar to make sure that two decoder is interchangeable?
So the latent space are like separated. So let me show the. So when we train here we go. So we can see that we have a latent space for the phase B and latent space for the phase A. So we don't really care when we train those like two things, right? Because this is completely separated. But after, like when you want to do like the swap, here we just swap the decoder, right? So what's happened in the training is we just do a sequence of training between phase A and phase B. So we do encode phase A, and after decode phase A, and after we encode phase B, decode phase B, and after we swap the decoding.
So the encoder is share weight. The encoder is the same.
The encoder, yeah, the
Okay.
encoder.
Okay, thank you.
I have a question about training. If I start with the 3D model, why would I want to use an AI to generate the augmented dataset when I can literally just render with in-game lighting and in-game settings those 35,000 images? I mean, I would expect, and this is my question, like if you have some expectation or some testing that the result with the game lighting and game settings will be better than an artificially generated image with a set of lighting generated by the AI.
Yeah, so of course, you can like, take your engine and generate different lighting condition. The thing is, we believe that this, in terms of work, this is like a lot of work, right? So it means that for each engine, you have to do this kind of thing. Where here, in this kind of pipeline, because this is outside of the engine, this is like pretty easy. And actually, this is like completely automated. So this is just a question of how heavy your work will be. And yeah, that's it.
Yeah, so the point is that you want to like something engine agnostic that you can just plug anywhere,
Yeah.
and that's it. Okay, thank you.
I think another thing is a lot of neural technology I kind of look at as a form of data compression. And one way to look at this tech is if your training data ends up being like a light field that you're rendering or you're capturing from actor performance. And really training is a matter of just building a key that we can then search that with. So, yes, I mean, if you're in a case where you can render the image you want, then no, there's no reason to do any uplift. But the idea is that we can actually kind of capture something that's a little bit higher fidelity or with features that are harder to model. Subsurface scattering, poor detail that is kind of hard to capture on characters' eyes, and kind of thin hair features. Stuff that you could theoretically model, but that in practice, if you could just reproduce it from an actor performance capture instead, would be much faster in the pipeline. So it's partially like a render fidelity tool, but also it's a render fidelity per hour of artist work, if that makes sense.
Okay, thank you very much.
Hi. So two questions. Hopefully the first one is a quick one. why? So the autoencoder thing, do you need to generate from engine the like matching data set for the B heads, or you just use like the 15 poses?
So as of today, we have like a custom data set with like some like faces. We are working on having like a complete synthetic data set because what is good with a synthetic data set is that you can like control everything. And the thing is, the current data set that we use some like pictures, and so we don't control really like the angle and all that. We have like a synthetic data set will give us like the better control on all those angles, and also like give us like on the data set B like exact segmentation of the face because we are everything is synthetic, right?
Yeah.
So yeah.
Yeah. And the other one, I'm super impressed by the color correction, stitching, composite algorithm. I was wondering how does it deal with the like sharp angles where maybe the model shuts off, or maybe shadows? Do you need to do anything special with that?
Yeah, so that's actually a couple different parts. Shadows on the face, right now, the model will kind of tend to soften shadows. So if you've got, we had a couple cases where you had like a really hard shadow line across the middle of the face. It tends to turn into more of an ambient type. I mean, there's still a gradient there, but it's a much softer shadow. Yeah. That's something I think we need to think about more with training. Angle-wise, we didn't handle it, so if the character like turns their head around, the model will freak out. But that's something that you can account for by looking at the calibration data and knowing the validity ranges of the data. And then the only time it really has any problems is if the character's looking away, in which case you can just fade out the blended data anyways. Yeah. So in practice, there are problems, but they're pretty easily worked around, we think.
Cool. Thank you.
Okay, absolutely fascinating stuff. Impressive. I just have a quick question about the model itself.
Yeah.
You were talking about, warping image into training space, and it was using an affine transformation based on the face mesh. Now, that might not be an Onyx operation.
No, that we just do that in DirectX, CPU side DirectX math. It's pretty simple. So we create a vector from the left eye to the right eye. We find a center point in that, and then we do a line down to where the mouth is. So that gives us like a 3-point data, and then we just figure out what the rotation matrix is to match. Then we have like equivalent target points in our model space. So we just do a rotation and figure out the scale factor to match that. So it's a pretty simple operation.
Fantastic. And just to follow up on that, were there any custom layers which could not be, trivially exported to the Onyx format, which you had to handle separately?
Not really. No.
Okay.
The model in terms of architecture is pretty simple, encoder, decoder, so everything was exported nicely.
Okay, fantastic. Thank you.
Hi, so I'm an artist, and so a lot of the language goes over my head, but it's been super cool to see what you guys are doing with technology, and I just like thinking in greater applications. Right now, I can see you guys are training it on like kind of the typical human face, so I was wondering, like, as this tech gets more advanced, how's it going to handle like wounds or scars, or maybe like, are you going to go to like non-human alien faces? Like, where do you think this is going to go?
Yeah, so as of today, we can see that the result is like pretty, like the skin is pretty soft, right? So we are losing like high data frequency and all that. But obviously the goal is to have like the fidelity of the original character to be there. And so this is why we are working on like a more efficient model, and also try to reduce all those steps of like, having like some a data set of 45,000 images and all that, right? So simple it is, and we think that that after the result will be like better.
Okay, thank you.
As far as I understood it, you mask out the face and all the other objects to just render over the face again. But what if I change the hair of the character or put some other glasses on the character's face? Would you need to retrain the model, or
will it just adjust to the changes?
Yeah, we need to retrain the model. We did some experimentation. I mean, we want to do also some other experimentation where we can, for example, inject the texture of the character in the model at runtime, for example, to have like also more control from the artist, right? But as of today, if there's any change from the character, we have to retrain the character.
Okay, thank you.
Good.
Any more questions?
And we're about time.
All right, thank you.
That's it.